Welcome back, everyone, to the online Graphs and Matroids seminar. Today, we're happy to have Cameron Crenshaw from Louisiana State University. So take it away, Cameron.
All righty. Thank you very much, and thanks for coming. Before I start, can you guys see my mouse moving around? Okay.
Yep.
I don't have my hand. Well, I do have my hands, but I'm going to point at stuff. All right. So I'm talking about ordering circuits of matroids, and this is a large part of my dissertation, and it was all done with James. So the first thing that I will tell you about is what I mean when I say an ordering. So if you've got a set, just any old set, when I say an ordering, I mean arranging the elements of that set in a circular fashion, where what's really important here is which elements are next to which other elements. So technically, we call this a reversible cyclic ordering, which I will henceforth call just an ordering of the set. But cyclic because, of course, it begins and ends in the same place, and there's no real beginning or end. And then reversible because I don't care what direction you travel, there's really no direction involved here. There's just elements next to other elements. So we use the words adjacent for elements like 1 and 2 that are next to each other in this cyclic ordering. And elements like 3 and 5 are not adjacent to each other. And this adjacency and non-adjacency is really the information that the ordering has, that's what is being encoded in this ordering here. I might more succinctly represent this hexagonal ordering that I've kind of drawn here as this cyclic notation from algebra, where obviously after 6, you wrap back around to 1, and you can see who is adjacent to who in that picture. Similarly, just to reiterate my point, I could also have started at 3 and wrapped backwards 2, 1, 6, 5, 4 back to 3. It's the same cyclic, reversible cyclic ordering. It's the same ordering. So this is what I mean when I say ordering a set. Graphs give you orderings of their cycles. So something like 7, 3, 8, 6 is an ordering on the set of edges of that cycle. More importantly, graphs do this in a very particular way that we're interested in. They're consistent in a sense. And so what I mean by consistent is if two edges are adjacent in the ordering of a cycle, then they'll always be adjacent to each other in every ordering of every cycle that they appear in together, which you're probably thinking, duh. Similarly, if they're not adjacent to each other, then they'll always not be adjacent to each other in every ordering of every cycle in which they appear together. And again, duh. Hopefully by the end of this, you will be as impressed as I am with graphs that they just do this effortlessly. So here's 2 representations of the same matroid. We're interested in generalizing this idea of ordering the cycles in this consistent way, but to matroids in a larger sense. So obviously that means we're ordering circuits of the matroid. For graphs, they come with orderings and they work. Matroids, more generally, don't have some inherent, cyclic structural ordering that is given to you for these circuits. So that doesn't stop us from giving them orderings and attempting to do so in this consistent way. So we will call a matroid orderable if there's a consistent ordering of its circuits. And so an ordering of its circuits is an ordering that has been given to, or, it means that I have ordered each of the circuits and the whole ordering is consistent as long as the adjacency and non-adjacency is consistent through all those circuits. And this begs the question of which matroids are orderable. So right off the bat, obviously, every graphic matroid is orderable. You draw the graph tells you how to order the circuits consistently. From there, I think a natural place to go is to the class of binary matroids. And I think the first natural place any of us would go to try out a new binary non-graphic matroid would probably be the Fano. So this will be my example just to show you what it looks like to explore the orderability of a matroid. So let's see. Along the left side here, we've got this 3-element circuit 1, 2, 4. And the nice thing about 3-element circuits is there's only one way to order them. No matter what I do with the rest of this matroid, this circuit is ordered 1, 2, 4. It's the same as 2, 1, 4. It's the same as 4, 1, 2. All three of these elements are adjacent to each other. It's the only way to do it. Same is true of 1, 5, 7. Same is true of 1, 3, 6. And now I come to just some 4-element circuit. So I just grab this one, 1, 2, 3, 7. And we're going to focus on the element 1 here. The first circuit, or the first ordering, tells me that 1 has to be adjacent to 2, no matter how I order this matroid. And the second one tells me 1 has to be adjacent to 7, and 1 has to be adjacent to 3, which means to order that fourth circuit, I have to somehow order it with 1 adjacent to all 3 of the other elements. And it can only be adjacent to 2 of them. So that right there is telling me that this matroid isn't orderable. And maybe that's what I should have called my example in the first place, but I didn't want to spoil it. So the Fano isn't orderable. Alrighty. So we're looking to go from graphic out to binary. And I've got here all of the excluded minors you might want. So this is specifically the list of series excluded minors, but it's got the parallel minors and the regular excluded minors in this list. And so in your exploration of, or I guess in my exploration of starting with graphic and trying out some non-graphic binary matroids, this is, I think, the natural set to start with. We've already seen that F7 is not orderable, and it turns out that none of these matroids is orderable, which is progress right there. If I require that every minor of a matroid be orderable, then the matroid's got to be graphic because the excluded minors for graphic aren't orderable. And the same is true if I require parallel minors or series minors. This isn't a very deep theorem, but it is a theorem and it's progress, and that can be hard to come by in orderability. So progress. But at this point, we took one step outside of graphic, and no matter what direction we stepped, we ran into a wall of not orderable. So hopefully, like I was, you probably have this sneaking suspicion that the answer to which binary matroids are orderable is just the graphic ones. So to get there, the idea was take those series minors, which we know aren't orderable, and then show that their series extensions are not orderable. So the way to think of series extensions, particularly in the context of orderability, is that 2 elements are in series exactly when they belong to the same set of circuits in the matroid. So this is, I think, standard. A single element series extension means that you've added an element in series to another, and a more general series extension means that you've done some sequence of these single element series extensions. What this means in orderability is you've got a matroid and you've got all of its circuits in front of you. And if you're trying to order that matroid, but you're working on series extensions, it basically means that you have copies of the elements, because every copy is just some element added in series with whoever you're making a copy of. So given the relative tractability of working with series extensions, combined with this observation right here, which is nothing more than if you can order a collection of circuits, and you can certainly order a subset of those circuits, so you're closed under deletion, putting those two things together gives us the strategy here. If I've got a binary non-graphic matroid, then it's got to have one of these as a series minor. So it must have as a restriction, which would be orderable. I guess if a non-graphic matroid was orderable, it would have to have an orderable restriction, which was a series extension of one of these matroids right here. So long as I can show that these don't have orderable series extensions, then I win. Binary plus orderable will indeed imply graphic. I wouldn't want you to miss out on all of the fun that is checking whether a series extension is orderable or not. So I'll just run through F7 again. So I'm going to use N to denote some series extension of F7, which again just means that I'm using the same circuits as F7, but I'm allowed to use copies of the elements. The first thing that you got to rule out when you do this is this thing that I call surrounding. So suppose in some circuit of N, I have ordered it in a way where this blue 1 here is surrounded by two copies of 2. So 2 prime is just an element added in series with 2. It doesn't matter which circuit that contains 1 and 2 this is happening. I'm just saying suppose that 1 has been surrounded by 2. Then in the circuit of N that corresponds to 1, 2, 5, 6, that same blue 1, since it is surrounded by 2 2s, is certainly not adjacent to anything else. So in particular, it's not adjacent to any 5s. And in the circuit of N, which corresponds to 1, 2, 3, 7, 1 is surrounded by 2s, so in particular, it doesn't touch any 7s, which means when I go to order this circuit of N corresponding to 1, 5, 7, I can't touch any 5s and I can't touch any 7s if I'm consistent with the previous circuits, which means there's no way to order this circuit right here. And so all this has done is ruled out that 1 is not surrounded by a pair of 2s. But now you can use the symmetry of the object to say that really 1 couldn't have been surrounded by any pair of elements of the common series class. And at that point, now you can use the original argument. So for example, in the set 1, 2, I'm sorry, in the circuit 1, 2, 4 of N, this element, this blue element 1 is going to have to touch both a 2 and a 4 because it's not surrounded. And it'll have to touch at least 1 and at least 1, 5 and 1, 7. And it'll have to touch at least 1, 3 and 1, 6. And then you won't be able to order 1, 2, 3, 7. So the same argument now works once you've ruled out the surrounding thing. So here's the binary excluded series minors for graphic. The one I just showed you was a nice one, worked out very nicely. The others take a little bit more time. I spent a good portion of a summer checking all of these, and it turns out that these matroids do not have orderable series extensions. The dual of F7, unfortunately, does have orderable series extensions. So here's F7 dual just so you can see the circuits. But what I've given you here are the orderings of the circuits of an orderable series extension of F7 star. I called it O1 for orderable number 1. So these primes are telling you that 1 and 1 prime are a series pair. 1 prime has been added in series with 1. So it's just copies of the elements, like I was saying. I'll give you 10 minutes to check. This is indeed a consistent ordering. I'm just kidding. I'm not going to put you through that. But it works. It's consistent. It's in the paper if you want to look at it. Really, the important thing to take from this is that you can see the surrounding thing that I have done, where I'm sort of removing elements from the equation by buffering them with, a pair of 1s or a pair of 2s. And that's, I mean, if nothing else, it really was just convenient and it made finding this ordering easier. But this was the result of trying to prove that this matroid didn't have series extensions, failing for 2 or 3 days, and deciding, maybe it does, and finding one. So that pair right there was our first set of evidence that orderable matroids are not closed under, in particular, series contraction. But obviously, you can't contract things at all. It really just ruins the game for orderability. M star K5 also has an orderable series extension, and this one's a little worse because now this is a pair of regular and co-graphic examples, and so restricting yourself to that tighter class of matroids isn't enough to fix this problem. But of course, those two problems that I have trotted out for you that ruined the party of binary plus orderable makes graphic, they both had series pairs in them. So they're certainly not 3 connected. And we have yet to find an example of a 3 connected binary matroid that is in graphic, that is orderable, that is in graphic. I don't know if such a thing will be hard to find or not. It was hard for me to find because I was checking all of these things by hand. So if I was to come back to orderability, I would most certainly come back to this right here, and I would just be checking. I would learn how to use Sage, and then I would be checking lots of matroids for orderability, just to have a bunch more examples. We have made progress though, and that looks like this. So a 4-connected orderable regular matroid is indeed graphic. I'll say just a few words about it to tempt you into thinking that it maybe isn't as hard as it looks. So a binary matroid is regular as long as it doesn't have a series minor isomorphic to F7 or F7 dual. And having a series minor isomorphic to F7 is not a problem. This is really what we proved. A four-connected orbital binary matroid only needs to avoid having F7 star series minors, and then your graphic. So we're actually very close to just getting this in general for four-connected orbital binary matroids. The progress that we made on this was due to this particular sledgehammer that we hit it with, which was suggested to us by Jim Geelan. Thank you very much. So this is a paper from Seymour called Adjacency in Binary Matroids. So, naturally, we had looked at it, but hadn't thought to try to apply it in this way. So opposite elements in a K4 are just a matching. And then, his result was that a four-connected matroid with no MK4 minor with a particular pair of elements as opposite means that the thing is either graphic or co-graphic, and those elements share an endpoint. But this is what we use to get the progress that we have in this case. So now we're going to transition out of binary into non-binary. What I've given you here are two statements of the exact same theorem. So a matroid is binary if it doesn't have a U24 minor, and it's non-binary if it does have a U24 minor. The reason that I've done this is the first one, in the world of binary, tells you that a certain structure is not present in the matroid, which hasn't proved very useful in terms of orderability. Being non-binary means that a certain structure is present in the matroid, and that has turned out to be much more useful, so much so that we've completely characterized which non-binary matroids are orderable. It all begins with this little observation here. If the rank of your matroid is no larger than 2, then your circuits can't be any bigger than size 3, which means you're just not big enough to fail. The elements will always be adjacent to each other. You're always going to have a consistent ordering. So you're always going to be orderable. In particular, that means that U2n is always orderable. And these long lines are the seeds from which all of the non-binary orderable matroids will be grown. So now I tell you how to grow them. First is parallel path addition. And this is not something restricted to non-binary matroids. You could do this to any old matroid. But what I'm trying to depict on the left here is just a graph which represents the matroid simply because it makes my explanation easier. The big oval is the rest of the graph, and this is just some series class sticking off the side. So to add a path in parallel, you take a subset of a series class, which I'm going to call P for path, but it's just a subset of a series class. And you make a copy of that set, which is then added in parallel to the existing subset of the series class. And so that looks something like this in the graphic case. This is perfectly well defined, even when the matroid isn't graphic. It just makes for a nice picture, I think. And the idea here is that if you started with something orderable, the circuits of the new thing are all of the circuits of the old thing, plus some new circuits that instead of using 1, 2, 3, 4, use the copy set 1 prime, 2 prime, 3 prime, 4 prime. And you order them the exact same way you ordered the ones that used 1, 2, 3, 4. You just put 1 prime in for 1 and 2 prime in for 2. So orderable. And even better than that, not only does starting with an orderable matroid give you an orderable matroid, but the original is also a restriction of the new one, which means that, they're equivalent in terms of orderability. So this is parallel path addition. And this is always something you have to worry about if you want a class of orderable matroids. The next one is balanced series extension. So I had said that doing a series extension is like making copies of elements. A balanced series extension means that you make the same number of copies of all of the elements that you started with. In this world, that's important because a series extension of U2n is orderable if and only if it is balanced. And this should say, this is for n at least 4. If it's 3, you don't need to be balanced. But so this is true for n at least 4. And we get a lot of mileage out of this little proposition right here. Just to give you an example, so with U24, we're just taking the original 3-element circuits and repeating them however many copies you've made. So that, I guess that would be K. Yeah, that'd be K. And then you just shuffle around which elements, which copies are in which series class, and you can make this work every time. I originally, in the paper, had a proposition that said that every balanced series extension of every orderable matroid is orderable. And I had a proof of that, which was so convincing that it got published. And then I discovered maybe 3 days before my defense that the proof didn't work. But it doesn't mean that it's not true. I don't know if it's true or not. I just know that the proof I had didn't work. So I'd kind of like to know in general, if you start with something orderable and do a balanced series extension, is that still orderable? It's certainly true for these matroids. I don't know if it works in general. And again, I don't know if this is going to be hard. It might be easy to find an example. I just don't currently have one. And the proof I had was convincing enough to be published, and it was definitely wrong. Okay, so we have balanced series extensions of U2N. We have parallel path additions that you can do. So for this class of non-binary matroids, we're going to have to include all of these things. And it turns out that that's everything. So if you've got connected, because connected doesn't, restrict to connected components. So for a connected non-binary matroid, you're orderable if and only if you're obtained from a balanced series extension of U2N by a sequence of parallel path additions. And I will give you an idea of the proof here. So we take the Cunningham-Edmonds canonical decomposition of the matroid. And the very first thing that we do is show that there's exactly one non-binary vertex label. It must be isomorphic to U2N for n at least 4. And the degree of that vertex has to be exactly n. In this case, n is 4 in my little picture here. That's the majority of the work. That's the majority of this problem, is this 3 connected non-binary orderable matroid stuff. The next thing you show is that all of the other vertices are either circuits or co-circuits. That's most of the rest of the work. From there, so you can assume that the thing is simple, because if it wasn't, you could add, first off, it's connected, so it doesn't have any loops, but you can add parallel edges back as the operation parallel path addition of a path of size 1. So the rest of the process here is just removing stuff in a way that can be fixed using parallel path additions. And if you had parallel elements, you could add them back that way. And that's how I know that the leaves of this picture are circuits rather than co-circuits. Next, we start taking those leaves, which are circuits, and proving that they're the same size. And that comes from that proposition that says that a balanced series extension of U2N is orderable. A series extension of U2N is orderable if and only if it's balanced. That's what I'm using to say that these things are the same size. I'm not going into a lot of details, but you get a lot of mileage out of that little proposition. So you prove that these leaves are circuits of the same size, and then you can take one of them away because it could be added back using parallel path addition, because it's parallel to the other leaf attached to that same vertex. So the process now is pruning these subtrees that hang off of the red vertex, pruning them down to cycles like this. And now what you're looking at is a series extension of U2N. And it's orderable because when you undo a parallel path addition, you're still orderable because you're a restriction. And so this is now an orderable series extension of U2N, so it had to be balanced. And that's how we know that you start with a balanced series extension of U2N, and you do parallel path additions to get the rest of the matroid. All right. Next, we have theta orderability. So this is a theta graph, in case you haven't seen a theta graph, but I feel confident that you know what I mean when I point at the thing. This is obviously the graphic version, but in a matroid, if you have some subset that you restrict to, and that restriction is isomorphic to the cycle matroid of this graph, that's what we would call a theta graph that lives in a matroid. The series classes of the theta graph are what we call its arcs. And theta orderability is about requiring the ordering to respect the arcs of the theta graph. So more specifically, this is just a random ordering of the numbers 1 through 7. This little section, 2, 3, 4, 5, is like a little continuous set that every time 2, 3, 4, and 5 appear together, they're going to have to appear in exactly this order because of consistency. And that's what we call a block. So a consistent ordering of a matroid is a theta ordering, so long as every arc of every theta graph is a block in that ordering. So I'm requiring, not only are you doing this consistently, but every arc of every theta graph has to appear sort of together in this consecutive way. And so you're respecting the arcs of the theta graph, which I think is, I mean, it was James's idea, but I think it's another kind of natural thing that you might want. It turns out that this one works out just like you'd hope. Binary matroid is theta orderable if and only if it's graphic. Yeah, so the process we used to prove this was exactly the one that I described earlier for binary matroids in general, where we have excluded series minors. We showed that they don't have theta orderable series extensions, and you get the proof that way. We then discovered that Wagner did some stuff on these things he called incompatible arcs. And it, you know, there's incompatible arcs aren't on the quiz or anything, so I don't want to get too into it, but I use the same word arc because the way he uses the word arc is the same way that we use the word arc. They're really just arcs of theta graphs. So what this picture is showing is you've got 3 arcs that live in the same circuit, and they're incompatible if they have non-empty intersection and none of them is contained in the union of the other 2. So compatible would look like this. You got to have at least one of them contained inside the other 2. And if you were to draw this out sort of like elements in a circle of the circuit, you end up sort of squeezing them together, and it starts to look a lot like orderability and arcs appearing as blocks. And indeed, the 2 are equivalent. And it was similar enough that instead of reinventing the wheel with our proof, we really just routed and rewrote the thing to route through what Wagner had done instead of redoing it. But not a lot to say about theta orderability because we solved it, so I don't think it's as interesting. Unique orderability, though, is, in my opinion, very interesting. So a matroid is uniquely orderable if it's got exactly one consistent ordering. And I'm very strict about this one ordering thing. So I think showing you some not uniquely orderable things might help. So the thing on the left, this is just a 4-element circuit. I could order this as 1, 2, 3, 4, and I can't screw it up because it's the only circuit. So it's consistent. I ordered it. But I could have done it as 1, 3, 2, 4, and of course, you know, there's no other circuits to be inconsistent with, so it's a consistent ordering of the circuit. And I considered a different ordering because in the first one, 1 and 2 were adjacent. But in the second one, 1, 3, 2, 4, now they're not adjacent. And that's how strict I'm being with this is a different ordering. You know, similarly with the second one, and you know, you all are sharp, so I'm sure that you can see that in the second one, for example, even though I've added this element 5, I can do things like Whitney twists and swap 3 and 4. And what I get is, you know, an isomorphic graph, but it's a different ordering because now 1 and 3 would be adjacent, whereas they weren't before. So this is just a visual way of showing you that I can create new orderings of the same matroid using Whitney twists, even in the graphic case. There are, of course, uniquely orderable things. So U2N, for example, when all of your circuits are size 3, everybody is adjacent. There's only one way to do the ordering, make everybody adjacent. MK4 has some larger circuits, but there's enough 3-element circuit that one's uniquely orderable. I included MK33 because now there are no 3-element circuits, and so it's a little more interesting. But the pattern continues that, 3 connected, uniquely orderable, not 3 connected, obviously not uniquely orderable. And again, I'm being very, very picky about what I consider different orderings, which I would hope means that I'll get some results from this. Because if I'm being lackadaisical, it's probably harder. And if I'm being very strict, it should be hard to do. Even in just the graphic case, we haven't been able to prove that the 3 connected matroids are the uniquely orderable ones. And it bugs me, I'll say. One direction here is easy. If you know that the thing is uniquely orderable, then it's got to be 3 connected because, and again, I'm only talking about graphic matroids here. In a larger context of just matroids, good luck. But even just assuming that the thing is graphic, if you've got this, if you had like a 2 separation, that's going to show up as a 2 vertex cut in your graph. That's a place where you can do a Whitney twist. So if you're not 3 connected, you're certainly not uniquely orderable. But the other direction of starting with 3 connected and showing that you must be uniquely orderable, we've worked on it, but we don't have it yet. So I'm showing you this example down here because I've described how I can do Whitney twists and create new graphs with different orderings for the same matroid using a Whitney twist, which is telling me that you got to be 3 connected if you want to be uniquely orderable. This is a little bit worse, however. Obviously, I can do my twists and I can permute A and B, C and D, and E and F, however I like in an ordering. But this haunting little ordering right here is one that cannot be created through Whitney twists. The series pairs aren't adjacent to each other, and it's consistent. And I don't know that it's interesting because it's still very small, but even in this little case here, spooky things like this happen where not only is it a new ordering, but now it's one that can't even be produced by twisting around the graph. And this is the nature of orderability, really, that stuff tends to go like this. So this is uniquely orderable matroids, and I'd really like to know that, at least in the graphic case, that the 3 connected stuff is the uniquely orderable stuff.
Okay, Cameron, when you say if M is uniquely orderable, then M is 3 connected, I guess you can allow the thing to be disconnected, right?
Oh, yeah. I'm sorry. I should have said that everything here, I'm always assuming that you're connected, because if you're not, you just restrict to connected components. Yeah.
Yep. Okay. Thanks.
Yeah. Sorry. Thank you. All righty. We have also thought about uniquely theta orderable, and just like before, theta orderable stuff is very well behaved. Turns out that these are just the 3 connected things. But even here, this is only for the graphic stuff. So let's see. Oh yeah, I kind of like the way that this goes. So you've got a graphic matroid, you've got a pair of edges. What I want to show you is that the adjacency in the ordering has to be the adjacency given by the graph. So here I've got the graph that represents the matroid, and I've got some pair of edges that meet at a common vertex. If you delete that common vertex, then you're still at least 2 connected. So there is some cycle that contains those other 2 endpoints, which means in the original graph, that pair of edges was the arc of a theta graph, which means that it has to be a block in your consistent ordering, aka those edges are adjacent with each other. So long as you're 3 connected and you have a consistent theta ordering, the adjacency given in the graph is the adjacency that you'll have in your ordering, and that's how you get that part. All righty. So to wrap it all up, this went much faster than when I practiced it. To wrap it all up, I'd like to summarize by giving you a list of my most wanted questions here, things that I would really like to know. And this is far from all the questions that we had when we worked on the stuff that we weren't able to answer. I'd really like to know if the reconnected orbital binary matroid is just a graphic matroid. And I think the way to resolve that is to just do more examples. I think there'll be a lot more to learn there. So I, again, would come back with Sage and try many more examples. Just checking, are these things orderable or not? I don't know whether this would be hard to prove or not, because the matroids that I was checking, I was doing by hand. Are balanced series extensions of orderable matroids orderable in general? Again, there might be an easy example, but these things don't tend to be easy to find in orderability. And then lastly, it just feels so obvious that in this graphic case, the three connected stuff has got to be the uniquely orderable stuff. And it did feel like we were making progress on that. There's a paper where they describe operations that you can do, I think starting with wheels, but there's operations that you can do, like adding a vertex adjacent to three existing vertices, little operations you can do to build up to the three connected graphs, and then just checking that each one of those operations preserves unique orderability was getting me somewhere, but eventually you just get to a place where you have no tools and it's hard to say where you should go from there. So these are just three starting points that I think I'm hoping to entice people to work on orderability and find these things out. So that's everything that I had. Thank you very much for listening to my talk.
Okay, thanks, Cameron. So on the round of three, let's all, on the count of three, let's all unmute and give Cameron a round of applause. So 1, 2, 3. Okay, and are there any questions for Cameron?
Sure, I've got a question here. Yeah, if you think about graphic matroids, when you have the adjacency relationship, then you can get these large classes that are every pair of which is adjacent, right? These correspond to the vertices. So do you get any kind of classes, or do you have special properties of the adjacency relationship that come up in the non-graphic case? Is anything interesting there?
I don't know that we've looked specifically at what sort of things happen with the elements that that happen to be adjacent in the ordering that you make. But it does kind of remind me of something we tried. So I said that I was very restrictive with what I consider unique orderings. Let me go back. So this feels very similar to kind of what you're describing. This example I gave at the bottom here, an ordering has adjacency information, and you could make a graph that represents those adjacencies. And so this graph right here is giving me an ordering of the edges, or of the cycles and the edges among them. And it's really just the line graph. Each edge would be a vertex, and they would be adjacent if they shared a vertex, aka they would be adjacent in the ordering. So the adjacency graph of the ordering I make would just be the line graph of this graph. If I do something like a Whitney twist here, then I don't change the isomorphism type of the adjacency graph of that ordering. But this spooky ordering on the right here has a different isomorphism type of its adjacency graph. So the one on the left, the line graph here is just a prism, a triangular prism. And the one on the right is, it's a complete graph on 6 vertices with a perfect matching removed. So it's an entirely different structure, isomorphism type of the adjacencies. I think this is the closest that I have done that is describing like what relationships are there between the elements which are adjacent to each other in this ordering.
Okay, thanks. That makes sense.
Any other questions for Cameron? maybe I can ask one. So for this conjecture, does it help to go to 4 connectivity or, even higher, or is it still hard to get anything there?
We didn't think about it. I think we were so convinced it had to be 3 connected that we're stubbornly decided that we will make it work. We didn't try 4 connected.
And is there any notion of orderability that lies in between the 2 notions that you gave, like the consistent ordering and then the theta ordering? Because that one seems quite a bit stronger.
Yeah, so I had a thing for a little while that didn't end up in the paper. There were things I called compact orderings. And so I think this is, I don't know if there's a picture here that'll do it. So imagine that you have the circuits of the matroid in front of you and that you want to do a series extension. So I'm going to take an element and split it. I'm making a copy of it, but I'm just going to leave it in place in all of the circuits it belongs to. And I'm just going to imagine that I'm cutting that element in half. And now there's 2 of it side by side. That feels like kind of an intuitive way of inserting a new element in a cheeky little way that you haven't upset the ordering too much. But even for something as simple as U24, a single little split like that makes the thing unorderable. However, if you had something orderable like that, so something orderable where you have a pair of series elements, you have a series pair that is adjacent to each other, and that's orderable, then you could contract them back into a single element and you still have a consistent ordering. So this is a context in which series contraction does preserve orderability. And so if you had an arbitrary matroid and you had an ordering in which all of the series classes appeared as blocks, that was what I call the compact ordering. And this was a way to preserve series contraction. And it didn't make it into the paper because you didn't end up needing it to do a lot of things that we were able to do. But that's another sort of notion of orderability that we did have.
Right. Yeah. Any other questions?
I have a question. Cameron, since you mentioned doing a whole bunch of excluded minor examples by hand, and you mentioned wanting to go into using Sage to actually check orderability, do you have any sort of algorithm in mind that works for checking orderability?
No, I was talking to friends of mine, and he was saying that he was making a lot of progress on a problem by just checking tons of examples and seeing what you got and what you didn't get as examples of the property he was looking for. And it sounded to me like orderability would be something that could be checked in that same way, but I haven't actually, thought about, the details.
I see. Did you use any particular way to do the things by hand, or is it always more of an ad hoc kind of argument?
James kind of described it as voodoo that I would do, because this was always our last resort. He would come in with all these excellent Matroid ideas, and I would end up, when we were trying to prove something and we would hit a wall and the Matroid theory wasn't enough to get us over the line, ultimately we would have to resort to what I call just writing elements in circles and seeing what's possible and what isn't. So the first time that I did all of these, it was totally ad hoc, but I got slightly more organized. And if you look in the paper, there's these things I call the EFG property and I think it's either the strong or the series EFG property. And this is basically a more organized way of checking like this. It's basically which elements appear together in so many different circuits and starts to rule out who can be surrounded by or adjacent to other people. And so this was kind of a silver bullet that worked across everything, but there was almost always a slightly shorter ad hoc way to do each of them.
Okay, that makes sense. Thanks very much.
Sorry, you were muted.
Other questions?
Are there some classes of graph? Can you? Yeah. The Matroid base of graph. I mean, some classes of graph. Do you have some classes of graph? And the Matroid of them, can you order well? Or how many order can be defined or define? You define one order, uniquely order. And another question, it's can be extended to the hypergraph setting, hyper style or something else, and that's it.
My headphones were cutting out. That's why I thought that Jorn was muted. So I'm going to switch my headphones and then please ask me your question again. 1 second.
Maybe I'll stop the recording now and then we can do this off the air.